Hello, everyone. Welcome to CPE 517-WS Digital and Computer System Architecture course. This is lecture 3. We mainly talk about instruction set architecture. The part 1 is what's the instruction set architecture versus computer architecture. We figure out what's the difference of both of them. And then let's move on. So first, some logistics. For this class, some of the slides will be adopted from the textbook slides from UC Berkeley of David Patterson, while other slides will also be used from Shen and Napsty and Howie from George Washington. So all the credits goes to the original authors and all the errors are mine. Reordering and modifications might be made due to a requirement of the flow of this specific course. Okay. What computer architecture brings to the table? And first, other fields often borrow ideas from computer architecture. We're going to show you what, okay? So quantitative principles of designs, we take advantage of parallelism, such as Flynn taxonomy, and these kind of ideas are also adopted by operating system folks like SIMD, MIMD, task parallel, data parallel. The principle of locality is very much used by storage folks and networking folks, right? So we'll always focus on the locality when we're doing communication. Focus on the common case, which is coupled with Amadas law. This is pretty much everywhere, right? So to review a little bit of Amadas law, we said we want to focus upon the common cases, or when we want to improve a portion, that specific portion should take a majority of the time, or should be the biggest part of all the other parts. Otherwise, we should focus on the biggest portion of that program, right? In other words, if you invest many resources on some trivial or portions that's not taking the biggest ratio, then you're working on the trivial part, then that's useless, right? Okay. And then the processor performance equation like CPI and IPC, like CPU time equals cycle per instruction, multiply instruction count, and then multiply cycle time. Those kind of chain rule, which I think we derived from mathematics. This is also used almost everywhere, right? We have careful and quantitative comparisons. That's actually very hard. Why? Because computer architecture is more like building a construction. Using quantitative methods to do comparison is absolutely very useful, like software, right? When can you finish this software? And then quantify those efforts. Those are very hard things and very useful. So we do bring those things in. That's why we say quantitative approach of computer architecture. We define, quantify, and summarize the relative performance by using benchmark and geometric mean across different benchmarks, if you still remember last lectures and course. Define and quantify relative cost, right? Define and quantify dependability. We have the 5 nines, if you remember the availability, mean time to failure, mean time between failure, mean time to repair. Define and quantify power and energy, okay? That inspires DVFS, dynamic voltage frequency scheduling, right? The culture of anticipating and exploiting advances in technology, right? Like in computer architecture community, people typically be in the first tier of explorators that goes to different new technologies like NVMe, SSD at very beginning, and then GPU, FPGA, ORAM, OVRAM, those kind of new technologies that are always tested by this architecture community. And the culture of very well-defined interface that are carefully implemented and thoroughly checked. This is exactly instruction set architecture, right? So ISA. We define this kind of instruction set architecture for the underneath hardware to implement, as well as the top level software to leverage. So I know we've been discussed about the different layers of computers. And right now, let's redo this again with a concrete example, okay? Assuming you have the high level language of C, where you swap the value between VK and VK plus one, right? So you assign VK to temp, and then you assign the value of VK plus one to VK, and then you assign the value of temp to VK plus one. This is a high level C++ or C language or Java, Python, all of them are very similar. And then you use the assembly code compiler to compile your program into assembly, right? So you first load the value from X2, I think it's V, the address of V, to T0, which is a register. And then you load the value of VK plus one, which is X2, 4. We're going to discuss this kind of addressing later today in this lecture. Load it into T1, and then you store whatever you loaded from in T1 to the X4, right? So the T1 previously is in X2, 4, you store in X2, 0. And then T0, which previously is loaded from X2, 0, you store it in X2, 4. This is like a swapping, right? And then further, you convert this assembly code into machine code 010101. It's like instruction set architecture. Then this kind of instruction is going to go through the circuits. Then they can use circuits to implement the idea. Instruction set versus computer architecture. You see here, instruction set architecture, or ISA, is only those interfaces, like instruction sets we use to run this computer. Where other aspects of computer design are called implementations. We insulate the implementation because from the instruction set architecture, because we feel those are very engineering and not interesting and not challenging. But today, computer architecture is way more than instruction set architecture, because we have to address the technical hurdles that are more challenging than those we think about before, like the implementation before of cache or parallelism is very simple, but right now it's significantly more complicated. Computer architecture is design and analysis. Architecture is an iterative process, searching the space of possible designs at all levels of computing systems. So we use the way of iterative process that at the very beginning, we have creative ideas, and then we find some of them are bad. So we keep refining those ideas until we arrive at a very good idea, right? This is how computer architecture evolves. Okay, so since we brought so many things to computer architecture to the computing systems, can you guys do a discussion about all of those assets, and also give us like your opinion about which asset is the most valuable to this community? Okay, use 5 minutes or 10 minutes to discuss about this idea. Okay.